באותו ווקטל פינים היו מסביבות שונות, ואז בהתחלה היה לנו עוד, עם הארץ יותר פחות כזה, אבל אחרי זה נהיה לא יותר ברור אותו דבר, אם נהיה...
השאלה אם הוא מוגדר כדי משהו.
לא, אני שואלת.
לא, אני לא נכון.
אני אומרת שזה הזמן כאילו, אבל זה התחלתי.
פשוט נקודה מהגרם.
כולם בהרצאה של הקומפיוטר סיינס.
מה זה ההרצאה של הקומפיוטר סיינס?
מישהו שמדבר על מחשבים קוונטיים.
זה עכשיו כאילו?
זה התחיל
זה מאוד מעט יבוא.
10 דקות? בכלל. טוב, תתחיל.
הם לא תכננו שתחכה.
ברור. טוב, האמת שנראה שבינתיים אנחנו יכולים בעברית, נכון? לא? Okay. You were obstructed. I didn't see the thing. Okay. So, we discussed now the source separation, the mixing problem. And let me first define formally the problem, and then we can discuss a bit. This was not so close to the whiteboard before. Okay, never mind. No, I think it's maybe a more. The source separation problem. Okay, so again, I will first define it formally, then we can discuss a bit why we're interested in it. Can also call it the mixing problem. So we have n sources of information, okay, variables, random variables, which I will denote by Si. And what I will assume is that the Si are independent. Meaning that the probability distribution over all the S's is a product over Pi of Si. Right? Now these functions don't have to be the same for each one of the source. The source can make its own distribution, but they're independent. And
What's the probability that the source will do something?
for any value, so for any set of values of let's think about these sources as just numbers, so the one-dimensional variables. So the probability distribution for any probability for any combination of values of these S's is a product of a probability for each one.
What's the meaning of sources?
It's just what I call it. So there are some sources of information. information. Okay, I will give some examples in a moment. But formally, these are just random variables. And what we also have is n observations, which I will denote by xi. And what I will assume about the relationship between the sources and the observations is the most simple thing that we can assume, that this is a linear relationship. So the vector x is some matrix times S. I will denote it by A transpose just because it's convenient for me. And this matrix is I will call it the mixing matrix. And it's n by n.
Doesn't have to be an no observation.
What?
It has to be n observations, or you just chose it like that?
Yeah, so I chose it like that. I will discuss it in a moment. Okay? How was the talk?
It was good. It would be nice to stay longer, but still have to.
So our goal, so this is what I would call the generative model. In the past, when we discussed the problem of encoding of variables, we assumed a more specific generative model, or somewhat different generative model actually, where the sources were Gaussian, but I didn't assume that they're necessarily, the observations were Gaussian. Here, the observations are generated from some independent variables linearly, but that the variables are not Gaussian, or not necessarily Gaussian. Now, the problem that I want to discuss now is, suppose that we observe for a while, we observe that for a long time many examples of these sources, of these observations, right? Can we infer what is the matrix A transpose? Or actually, why would I want to infer the matrix A transpose? Because then I might invert it and be able to, for each, if this matrix is invertible, then for each observation of n x's, I would be able to find the n s's. So let me just write that down. Our goal is to find the sources so we would like to find some y which is equal to some matrix W times X such that y is the same, I will write here in quotes for a reason that we'll explain in a moment, the same as S. But now what I mean by the same? So there are several things that we cannot hope to be able to do quite clearly. For example, if there's no, if I don't know anything about this probability distribution, I might find a permuted version of the S's, right? There's no specific order. So I don't care if my matrix W is such that I end up with a permuted version of the S's. I cannot hope to find the correct, be able to infer the correct order. There's nothing special about each one of the S's. Similarly, there might be a scaling, right? We might multiply. If I infer not S but 3 times S, that's still independent of all the other ones. So I cannot hope to find the S's beyond some arbitrary scaling. So what I mean by that is that I want to find a matrix W such that Y will be the same as S up to the permutation and linear scaling. Now, what are some examples where this might be relevant? So I mentioned at the end of the last lecture, we might have 5 microphones in this room and 5 people speaking. Okay. Now each one of the microphones will pick up a linear sum of the auditory output of each one of the speakers with a different amplitude, right? So it will be some method. We should define this matrix A transpose. And if we have 5 observations and 5 different speakers, we can hope that this matrix is invertible. And now the question is, can we find it? Okay. So this is one example. In the context of, in other contexts related to the brain, remember that our general context right now in the course is that we're talking about encoding of multidimensional variables. So I think one good example where we might hypothesize that this is something that the brain might want to do. In fact, nobody knows, but it's olfaction. So in olfaction, each receptor, olfactory receptor, is sensitive to various molecules, right? And so that's just one source of linear combination, and it's not linear, but let's imagine it is. And furthermore, if there are several sources of odor, each source of odors might emit several molecules, some linear combination of molecules. So we end up with an observation, which is the activation of receptors, which is some linear combination, perhaps of some independent sources. So maybe the brain might want to separate the different sources. So up to now, when I described why this problem is interesting, I mean, first of all, it's a useful engineering problem in many situations. But for the brain, we're talking about the fact that maybe it's useful for the brain to switch from a representation, the raw sensory representation, which might mix some sources, and identify the true sources if they exist in the world of information. So this is one viewpoint for why this might be important. Before we come to the next viewpoint of the question.
I don't understand why to assume that the number of sources is the number of
okay. You're really persistent about this question.
Yes,
okay. Just because it will simplify my analysis. There's no reason to assume that. No, I'm just assuming it here just for simplicity. Certainly you need a number of observations which is larger than the number of sources in order for this to hope that this matrix will be invertible, or that you will be able to need more observations than sources. But you can certainly be in a situation where you have more sources. But then it complicates the analysis a little bit, and I don't want to get into this in the little time that we have for this problem.
Just a relation maybe to the brain.
Yeah.
So like if you gave an example of multiple speakers,
Yeah.
is there like any evidence for the auditory system
No,
working
okay,
somewhat like
no. I mean, it is true that we are able to solve to some extent this problem. To some extent, right? We are able to listen to several speakers and somehow focus on one of them. But I don't think that the brain, I don't know of evidence that you can find in the brain a clean representation of the output of each one of the speakers, and we don't know how this is done. I am not aware of a clean example in the brain where we know how the brain solves this problem and how it solves this problem. But this brings me now to the second motivation, why I'm talking about it. And there we will see a clear connection with neural representation. And this is the general context that we discussed so far of encoding of n inputs in a sensory system. So remember that when we did this, the first conclusion that we obtained, even when you did the n by n case, was that that we assumed Gaussian inputs, and the solution was to, at least in the case where there was low input noise. In the case where there was low input noise, actually in any case, the solution was to first encode the principal components of the input, right? Now, why is it that it's useful to switch to the principal components? It's useful to switch to the principal components because for a Gaussian variable, the principal components are independent variables. So by switching to that representation, we're now looking at variables which are completely independent of each other, and if we encode now each one of them separately, we're not encoding the same information twice, right? Now, this might make us think that a more general principle is that when you want to encode n variables, you want to switch to the independent components if they exist, right? Now, for Gaussian variables, it's obvious. For Gaussian variables, you can always switch to the CC representation, to the principal components. These are independent components. Here we assume, but for non-Gaussian variables, if you just record several non-Gaussian, mutually dependent non-Gaussian variables, it's not clear that there is at all a linear transformation that will turn them into independent variables. So we are assuming it now. We're assuming that there are some sources of information which are independent and observations are linear. In that case, I argue, without proving it to you in detail, that if you want to encode n variables efficiently, we want to first switch to the representation in which they are independent. Okay? Now, this has been the basis for a theory that attempts to describe, to explain the receptive fields in the cortex in several areas, most importantly in the visual cortex. So I mentioned to you that the receptive fields in V1 are Gabor functions, more or less. So these receptive fields are kind of look like things like this. They have certain spatial localization, but they're oscillatory. They have a certain kind of various orientation. And it turns out, I will not go into the detail right now, but it turns out that if you imagine that perhaps a visual scene is a sum of the independent components and you try to infer them using techniques that we will now study, you end up with the matrix like this, more correctly, a matrix like this, which takes the inputs and translates them into the presumed independent components, which describes receptive fields which are similar to what you observe in the cortex. Of course, visual scenes are not an independent a linear sum over Gabor functions with independent coefficients, but it is an approximation. So maybe I will get back to that topic a bit later, because now I just want to analyze this problem.
Okay. This problem can it also be actually like cases that X and S are not in the same dimension?
Yeah, so it is possible. Again, I mean, you cannot really, usually you cannot hope to solve the problem if you have a smaller number of observations than the number of inputs. But more generally, you can solve it if you have a larger number of observations. Now, there are several things that in addition to the fact that I assume that it's n by n, there are several other simplifications that I made here compared to what we did before. In this description, there's no noise, right? No noise. It's n by n. Is there any other simplification? No, I think these are the main things. But of course, so now imagine that of course, if there's noise will change a little bit how you want to infer the inputs. There won't be one-to-one correspondence. You want to, I mean, now in this formulation, given the inputs, there's a clear value of x, and then there's a clear way to get y out of x. But if there's noise, maybe you want to take that into account and make the best estimate of x based on the inputs, which is might not be exactly the same as the inverse of this matrix. Okay, that's one thing. The other thing is if you have more than n observations, okay, you have n inputs but more than n observations, because of the noise, they will not be precisely compatible with just inverting the matrix. You have to think what is the best way to reduce from the larger number of observations to the number of solvers, and I just don't want to get into these issues.
Are we assuming, I'm not sure about the framework, are we assuming Gaussian distributions? Or
No, okay,
we're not assuming it.
we're not assuming it, and in fact, the next point that I want to make is that we cannot assume Gaussian distributions.
Oh.
In other words, as you will see in a moment, if we assume Gaussian distributions, it is impossible to solve this problem. Okay? So this is actually what I want to point out. Okay, it sounds like maybe it is possible, right? 58. Okay, I will show you that it's wrong.
Gaussian distribution of X or?
Yeah, of X. But know that if X is Gaussian, if S is Gaussian, if each one of the S's is Gaussian, then X is also Gaussian because it's a linear combination. It's an n-dimensional joint Gaussian distribution. Okay, so
the matrix A
some matrix. Of course, it has to be invertible in order for this problem to be solvable, right?
So you assume it's random or what?
I don't assume anything. Now, when I say solve, there are two things that you might ask. I mean, you suppose first A has to be invertible so that if you know X, you can infer Y, so that you can open you want W transpose to be the inverse of A. But solving the problem now, what I mean by solving the problem is not just the ability to inverse, but the ability to infer what is the correct matrix based on the statistics of the data. So this is really what we want to do. So I will just show you a very simple example. So in order to point out that for Gaussian variables this won't work. So imagine we have just two Gaussian sources. Okay, so each one of them is Gaussian. For simplicity, I assume that the mean is 0. Okay, so one of them has a distribution like this. This would be S1. This would be P of S1, and we'll have an S2, P of S2, also a Gaussian, maybe with a different mean. Okay, both Gaussian. And now let's imagine that my matrix A transpose is the following matrix: 1, 1, 0, 1.
The same, right? 0.
0. Okay, so what does this mean? If this is a matrix, it means that the vector x1, x2 is x1 is s1 plus s2, and x2 is s2. Okay, so I can think about it as the following: it's the vector s1, 0 plus the vector s2, sorry for okay. So now what can we expect? How will the distribution of the x's look like? So let's look at the distribution. So we can think about the x is a two-dimensional variable. So I want to draw the distribution of x on a two-dimensional plane. So let's start with, and it's the sum of these two contributions. So that this contribution, so now I'm drawing like a density plot of P of x1, x2. This is what I'm drawing, P of x1, x2. And but I want to draw it as a sum of the contribution from this and the contribution from this. So if we had just this, how would this look like? Where will the values of the x lie on this plane? Only on this line, right? Because this is always 0. So it's kind of the values of x would lie only on this line with some probability distribution which looks Gaussian, right? I mean the values. I mean this should not be. I'm just overlaying on it. I just want to represent what is it. It's more dense here than here. Now, what about this contribution? Where do the values lie of x lie if it was S2, S2? On the diagonal, right? Okay, so it would be something like this. With, again, I'm overlaying on it. It's more dense from here than here. Fine, so what do we get? What kind of distribution will we get when we sum these two? I wish I had more space here. Okay, I will do it here. So P of x1 and x2 will be, I know that it's a Gaussian distribution, right? It has to be, because we just discussed the fact that it's a joint Gaussian variable. How will the contour lines of this joint distribution look like? What do you think they will look like? So the contour lines of a Gaussian distribution is always an ellipse, right? And how will this ellipse do you think look like? When you sum a variable, you always, each observation of x1 of 2 is like drawing a vector from this distribution on this line and adding to it a vector drawn from this distribution. So how do you So, okay, the problem is that when you go like this, I have no idea what you, yeah, it's a kind of diagonal. We expect that the distribution of X will be, you know, something like this, a Gaussian which, where the contour lines look like this. Okay, so now remember that we discussed the fact that when you take a Gaussian variable, a prescription for getting independent variables is to take the principal component. But what are the principal components here? The principal components would be a projection of X on these two axes. These are not x1, these are not the original s1 and s2, right? The original s1 and the s2, for example, s1, s2 by definition is x2. So if I wanted to get the original s1 and s2, I should have just taken x2 as one of my variables. But if I do the principal component analysis, it tells me to take some other combination of x1 and x2, this combination and this combination. None of these two combinations is simply x2. So where I have, now this is a bit weird, right? What's going on? Any ideas what's going on? Okay, so why are there other solutions? So you're right. There are many other different. The principal component, taking the principal components of this distribution, gives me one option to get two independent variables out of x1, x2. But it's not the only way. It has to be. We now see that it's not the only way. Why it's true that there are other ways to do it? In a linear combination.
Unitary transformation.
Yeah, so it has to do with this unitary transformation that we discussed previously. Now, the unitary transformation is applied after you do some other transformation. So in this case, what's going on is the following. This is the distribution of X, right? And now I'm free to do the following. I'm free to do one linear transformation, which will just kind of squeeze this in this direction, okay, such that I will get a circular distribution. This is a linear transformation. After I do that, I have a completely circular, completely symmetric Gaussian distribution which is completely symmetric in any direction. And then whatever two choices of vector components of projections that I will choose will be principal components of that distribution. A circular Gaussian, in any direction, it's the principal component. So I could transform this into a circular distribution, and then I could choose the projections on any two orthogonal directions, and they would be independent variables. Then I could even scale them if I want. In this case, we don't care so much about scaling because by definition. But so you see that actually there are many linear transformations that I can apply to this distribution, an infinite number, which will all give two independent variables. Okay? And therefore, inherently, if the inputs are Gaussian, I cannot hope to find the correct combinations of them. There are many different combinations. You can mix them, Gaussian variables, you can mix in many different ways to get independent variables. Okay? But this is a special property of Gaussian variables. Okay? What this teaches us, first of all, is that we lost something important when we assumed so far that variables are Gaussian. There's something inherently special about Gaussian variables which we need to think about. Okay? So now the claim is that if the sources F are not Gaussian, then it's wrong. Okay? Then it's not true anymore that you can find many different ways to combine them linearly such that you will get independent variables. Okay. So the next thing that I want to claim is that the mixing problem can be solved typically.
But didn't think that's impossible. Just show the PK is not a good solution, no?
No, I didn't only show
that it's not that it's a good solution. There are many, many different solutions, so I cannot distinguish between them. All I have to work with is my requirement that the variables y after I apply this matrix will be independent, right? But there are many, many different ways to do it. I can, in essence, after I do some rescaling, I can do any combination, any rotation, any mixing of the two variables will give me independent variables. Okay, so I cannot find the correct mixing.
And why you can do the rescaling?
Because it's a linear transformation, right? I mean, so imagine, okay, let's do the following. Start by rotating such that these two, so one linear transformation will rotate such that this will lie on the x-axis, this will lie on the y-axis, then do just a scaling of the x-axis, of the horizontal axis. That's another linear transformation. After that, you will end up with a distribution which is completely circular. Once you've done that, any two projections on any two orthogonal directions will be two independent variables. Okay? Alright, so I don't know how to prove this to you, but I will give you various arguments why this is true. And the first intuition, which is very important for this discussion, comes from the central limit theorem. The central limit theorem tells us that the sum of many independent variables is Gaussian. Right? And this leads us to the vague statement that I will write down now and will try to explain. That a finite mixture of independent variables is usually more Gaussian than the individual contributions. I will put a quote here as well. And we should probably avoid any documentation that I wrote this because it's not precise. I don't know how to, I mean, it's a very vague statement. It's not formally correct, but this is, nevertheless, it's somehow true. That if you, so what I'm saying is that if you take variables which are non-Gaussian and you sum them up, you tend to get something which is looks more like a Gaussian. And I will explain a bit more when, at least some situations where this is precisely true. Okay? And this gives us the hope for how we might approach the problem, or a direction for how we might approach the problem of the mixing. And this is that if we have indeed sources which are independent, they are non-Gaussian, we're observing some mixture of them, so the mixture is somehow more Gaussian than the sources, and we can now try to search for a linear transformation that will make our outputs less Gaussian. Okay? And you will see that this is the approach that we will take for the mixing problem.
Do we assume that they're identically distributed also, or just independently?
Okay, so indeed, it becomes more, this statement becomes precise if we have several sources which are identically distributed. We'll see that later. And for sources which are not identically distributed, it might not be even true. Okay? But often, it is often the case that the true independent sources have similar distributions, or at least similar, maybe not the same variance for each one of them, but at least the same way. They differ from a Gaussian in the same way. Let me show you some examples. Okay, so I want to still work a bit on this intuition, and to give you a bit of intuition for why this is.
And of course, this raises this. In addition to being wrong, this statement raises questions. What do I even mean by more Gaussian, less Gaussian? What is usually? So we'll discuss this to some extent. So let's imagine that you have a source which is looks like this. It's kind of very pointy. Okay, and let's imagine that we have another source which also has this the same distribution. So this will be P of x1, and this will be P of x2. S2. This will be S1 and S2. And now I want to draw the joint distribution of S1 and S2. So this is before the mixing. This is just the joint distribution. So how would this joint distribution look like? It's a bit hard to draw things like that, but the contour lines will be something like this. This will be the contour lines over which the joint distribution is constant. And so, of course, if we take a certain observation of S1, S2 and extract from it S1, so if our mixing was no mixing, if our matrix A transpose was simply a diagonal matrix, meaning that we remain with S1, S2, then we would extract back the S1 and back the S2, and the distributions would look like this. But let's now imagine that our mixing is actually generating that one of the mixed vectors, one of the x's, is a mixture of S1 plus S2. So imagine that this is one of our x's. How would the distribution of this x look like? The distribution of this x would look like actually, if you could kind of play with it and try to generate a distribution that look like this and do it. It will look actually quite in this case it would look something like this. If you go in this direction, if you go in this direction, you will get this distribution. If you go in this direction, you will get this distribution. But if you go in this direction, you will get something which is more smooth and end up looking more like a Gaussian. Okay, so here we mixed two variables which are non-Gaussian. It's not a Gaussian, but you get something which looks more like a Gaussian. Let's take another example which is even more simple. A similar idea, but yes?
Can you maybe relate this somewhat, like if we talk about this as speakers, like speaker 1, speaker 2, I'm not sure, I'm guessing.
Yeah, okay, so imagine,
Okay,
so first of all, speakers generate an output which is a function of time. But let's imagine that we have just samples of the wave function of each one of these speakers. So at any given time, we just have one variable.
Okay.
And this variable actually, if you would look at the distribution of the you take your sample at the computer, you take the distribution of the sample, it will not be Gaussian. It will be distributed about some mean, so I subtracted the mean. But it might look something like this. It will look more like this than like now this is if you have one speaker. Now imagine that you mix two speakers speaking at about the same amplitude. So this would be like something like this. Sum of two independent speakers. You will see that the distribution of the samples is more Gaussian than the distribution of each one of them independently. And we can expect it. One of the reasons we can expect it is that we know that when we set our limiter, that tells us that when we mix many of these, we end up precisely with the Gaussian. Okay, so 2 is in the direction of many. Let's do another example. Just the same idea, but a different distribution. So imagine that one of my S's is distributed like this, just a uniform distribution over some range, and the other one is also distributed like this. So here, in some sense, we have a distribution which is more narrow than a Gaussian. We will formalize this later on. Here, this is a distribution which is in some sense more wide than a Gaussian. So the joint distribution now of the S1 and S2. This is P of S1. This is P of S2. The joint distribution P of S1 S2. Maybe I'll just write this over here. P of S1 S2. How does it look like? it's a uniform distribution over this square, right? Uniform distribution. So again, if I now take any value of S1, S2 and project it, on the coordinates S1, S2, I will end up with this distribution. But suppose that I take a projection on this direction, meaning that I take an X, which is S1 plus S2. X is S1 plus S2. This was also 2 here. X is S1 plus S2. How will it be distributed? It has the largest probability, obviously it has 0 probability to be beyond these values. It has a kind of small probability to be here, right? Because any point along this diagonal will give us that X. It has the largest probability to be here. So the probability of distribution of P of X will look like this, right? Again, it looks more Gaussian than this. Okay, so but now, after these gains and intuition, what we really want to do next is to put some formal definition to the concept of being more or less Gaussian. Okay, it's for a very, in some sense, it's for a very practical reason. It's for a very practical reason because our approach. I'm looking for something that I wrote before, and maybe I erased it already, maybe it was here. Our approach to the source separation problem will be to look for, or one approach will be to look for a linear transformation of our observations such that after this, the outputs would be as least Gaussian as possible. Because of this idea that the mixing has made it more Gaussian, we need to make it at least Gaussian. So we need to have some formal definition of what is more or less Gaussian. So this puts us on a sidetrack right now where we want to quantify Gaussianity or non-Gaussianity, and this we will spend some time doing that. So I want to discuss a mathematical concept about distributions called cumulants. And so the discussion begins by being quite general. What I'm telling you is a very general way to describe probability distributions. Imagine that we have some probability distribution P of X. And one concept that you know is that we can define what is called moments of this distribution. And the moments are defined as follows. Mu n is defined as the average of x to the power n. In other words, this is an integral from minus infinity to infinity, x to the n, p of n dx. And so, meaning that mu 0 is, what is mu 0? It's the average of 1, so it's 1. Mu 1 is the average of x. Mu 2 is the average of x squared, and so on. Now you know that we're often interested in not in the average of x squared, but something which is more interesting in characterizing the shape of the distribution is the difference between mu2 and mu1 squared, right? The variance, so the variance is mu2 minus mu1 squared. So you see that the variance, for example, is a combination. So one thing which is useful to think about is that each one of these moments can have units. If we imagine that x has units, when this moment has no units, this moment has units of x, this moment has units of x squared. So the variance, for example, is a combination is a way to generate some quantity with units of x squared, but it's a very particular combination. It's taking mu2 minus mu1 squared. And we know that the variance is an important aspect of the shape of the distribution. So now the question is there a generalization of this to higher order things that characterize the distribution? And it turns out that it is, but we need to work a little bit to get there. So first of all, I'm going to define the following. And I'm going to, for whatever reason, you will see the reason later, I'm defining the function f of t. T is some variable, and the function is just defined by the fact that its Taylor expansion, the coefficients of its Taylor expansion around 0 are the moments. In other words, by definition, f of t is mu0 plus mu1t plus mu2 over 2 factorial t squared plus mu3 over 3 factorial t cubed plus, okay? And this function is called the generating function of the moment. It's just a name. When we say that something is a generating function of something, we mean that, it's just a term, it means that if we take the Taylor expansion of this function, the coefficients are the moment. Okay, but why am I doing this? First of all, is there any interpretation, probabilistic interpretation, or any interpretation in the field for probability functions for what f of t tells us? So it turns out that it does have one nice interpretation. So let's write down what is f of t. F of t, I just want to use now the definition of the mu's. So f of t, I can also write it as an integral of x going from minus infinity to infinity p of x, because that appears in the definition of every one of the moments. And then, for this term, I will have 1, right? This integral is just mu0. And then the next term will be x times t, because if I do the integral over x, I will get integral of x times p of x, that's mu1, and that's multiplied by t, so this is this term. And then I will have another term which is x squared t squared over 2 factorial. Again, if I do the integral over x, I will get here mu2 times t squared over 2, so that's fine, and so on. But what is this? This is a Taylor expansion of what? Of the exponent of x times t. So this is really the integral dx, p of x, exponent of x times t, where x is going from minus infinity to infinity. And therefore, this is what I would call the average of x e to the x times t under the distribution p of x. So it's not yet clear why am I bothering you with this function, but at least you see that you can interpret this Taylor expansion in this way. That, if I tell you what is p of x, now for every value of t, you can calculate the probability, the average of e to the x times t, and that is f of t. Okay. Now,
what's the meaning of t again?
It's a variable. So this is a function of a variable t. Just look at it as a function of a variable. Okay? Actually, I think it's a good time to take a break. Yeah. So.
פה זה יהיה ספור, כן, זה משהו דיבר שפה שצריכים, כאילו, זה כאילו כ10, גם כותב לא, זה יוניפורם. לא, כי פה זה אחיד, אין הבדל, אז למה X? רואה שפה יש לך מעט. אם אני סוכמת על זה, כאילו אני מסתכלת על זה סתם בתור, כאילו בציר, ואז את רואה שכאילו פה יש יותר. פשוט להפוך את ה... כאילו...
האם זה ציר, למה זה נראה ככה?
מה, הקיור הזה?
למה זה נראה ככה? כי פה יש לך כהה מאוד ופה זה בהירים. מסתדר?
לא.
אני חושבת
מה
שהרעיון
אתה רוצה שאני אראה לך? זה אני מבין את זה יותר טוב.
זה הסבירה לי.
כן, אבל איך את קוראת את זה? כאילו...
התוצאה היא יוניפורם.
כן. אז למה הנקודה הזאת היא יותר פרובליסטית מהנקודה הזאת?
פשוט האינטגרל כאילו על השטח, לא יודע.
אז זה פשוט x, נכון? שאנחנו מסתכלים מה ההסתברות של x, אז איך אני אקבל את x? זה סכום, אבל למה כולם?
יש מלא אפשרויות לקבל.
בדיוק, ככה אני מסתכל על זה, כי S1 ועוד, זה סכום שלהם, אתה יכול כאן, כדי לקבל את ה-0 אתה חייב לקבל בדיוק את ה-S הזה ואת ה-S הזה. כל S כזה הוא אותו יוניפורמי, אבל כשאני סוכם אותם, ככה אני חושב את
ואיפה
זה.
מסתדר כאן?
זה אותו עיקרון, זה יודע אותו דבר.
פשוט פה זה עם איזשהו... זה לא אחיד.
לכן אמר שזה y לא, פה אמר שזה נער.
ממה?
בגלל שזה...
זה לא זוכר שמה, אבל בגדול, תסתכלי. כן, אתה מסתכל כאילו מה...
אני מדמיינת את זה כאילו, כן.
כאילו נראה... פה יש אפשרויות.
נכון.
וכאילו, כמות האפשרויות גדלה.
אבל זה לא, אבל כאן זה לא אחיד.
כן,
כאילו הנקודה הזאת היא הנקודה שהכי מסתבר לקבל אותה, נכון? כי יש לי
גם מפה הפסיקו לקבל אותה וגם מפה.
ברגע שאני עולה למעלה פה, אז פה עדיין זה מאוד גבוה לקבל אותה, אבל מפה אני כבר התחלה. זה לא קרה, אני לא רואה את זה בעיניים.
אני צריכה לעשות את זה, אני מדמיינת את זה כהיטמפ, כאילו.
אבל מה ההיטמפ שלה? כאילו פה באמצע זה אדום כאילו, ממש?
פה זה זוהר, כן.
זוהר, ואז לאט לאט זה זוהר?
כן, כאילו לא ככה.
ואז איך את יודעת מה לעשות כאילו? זה לוקח את הערכים של ההיטמפ?
כן. אני פשוט
צריכה, אני
מדמיינת את זה כעצים, כאילו לא עצים, כהרים. ואז...
וכאן בריבוע זה באמת זה כאותו צבע כאילו? וכאן לכולם באותו צבע.
כן, פה זה פשוט ריבוע.
נכון.
כאילו במה כזאת, שזה לא משנה.
כן, זה הבנתי גם תוך כדי שהוא אמר לי, משהו דיבר על זה. אני צריכה עוד משהו ממך, אני פשוט מחדדת. אין בעיה. כאילו,
אני חייבת לצאת.
אפשר לשאול לך משהו?
כן.
נכון שהוא אמר על הסרגות, שזה כזה, כאילו כל האליקסר זה מעגל שניתחו אותו?
מה זה? איפה זה?
כאילו שהוא אמר למה זה בלתי פתיר?
הוא אומר שאפשר, לא באמת, אפשר לקבט אותו, אז אני מסכים על זה רק טרנספורמציה לינארית. אז בדפי את הפשוטתי, תעשי סיבוב, אז יהיה לך כאן, תעשי רק שונות, תקטיני את השונות בציר הזה, זה טרנספורמציה לינארית ואת תקבלי עיגול. עכשיו בעיגול, כל זה יכול ליצור אותו, תקחי כל זוג וליצור אותו.
כל זוג הוא
בדיוק.
אורתוגונלי ומעבר בפרופורציה.
כן.
אז יש כאילו אפשרויות, ואז כאילו בכם
אבל אתה לא יכול לדעת את השני, לא, יש לי אינטרסור שייצרו את המאגר הזה, נכון? זה לא כמו שחוקרות, זה איזה, אני הגעתי למצב כזה, זה מה שאני רואה. אני יכול להגיע למצב הזה במיליון דרכים, אני יכול לקחת כל זוג בלתי תלויים, לעשות סטרץ' לאחד מהם, ואז
כן, ואז אנחנו לא יכולים לעשות, כאילו לזהות את הסוף ספורה.
כן, בדיוק. זה מה שאני מבין, אני לא מבין את זה. זה של מיקי, לא?
לא, של עדי, יש להם אותו תיק.
איזה קטע?
לא ידעת את זה?
זה עדי.
זה דורון.
זה הייתה איזה קטע לא עובד.
שנים.
של התיק הזה עם מלא דברים.
הוא יודע תמיד כל פעם שהוא הולך עם התיק, הוא ידעת את זה עם אותו תיק, וכל פעם מרגישה שהוא לוקח אותו.
כן, מלא תיק, זה
לא, זה היה חדר כמו ישיבה כזאת. מלא פרקטים. כאילו עשו ישיבה. לא שנה אותה. זה היה מעניין במובן המקובל. מעניין במובן הקונספטואלי.
רואה לאן שואפים.
בדיוק.
אני מה אתה אומר על ההתחלה של גם?
זה שלא הבנתי הרבה, אבל הבנתי מה לא הבנתי.
גם את ההתחלה, לא יודע, אני הבנתי. ההתחלה?
לא, בסדר, אבל כן, כאילו, היה נחמד. להראות, אבל באיזשהו שלב, קראתי את זה לגמרי.
טוב, קשה, הוא לא, אני לא ממש גם. גם הרבה עבודה, אבל צריכים לפתור את בעיית שעה עם 10 רגעים. יאללה.
זה כן, זהו, פה הוא ישאל שאלות על זה. הוא אמר, מה אם אני יודע לענות על כל שאלה אפשרית בדרך חישוב בשנית? מה אני יכול לעשות?
לא, איך אני יכול להשתלט על העולם?
תגיד, זה דוגמה לשאלה השלושה. לדעתי יש תשובה. כאילו זהו, יש תשובה רק פרקטית לשאלה הזאת, ספציפית. איך להשתלט על העולם בהינתן זה. אבל איך אתה עושה כל דבר נוסף, או איך אתה עושה...
רגע, מה הסיבה שלך?
לא יודע, כאילו זה צריכים להיות קשורים לכספים, לדאוג לכך שכל הכסף בעולם יהיה אצלך. ואז אתה בן אדם חושב בעיה.
או שאתה מתחשב בבעיה, איך להשתלט על העולם, מה?
אבל כסף ההתפתחי פורמילייטית.
זה לא סוציאליזם. כסף כאילו זה דבר רלוונטי, כאילו כאן יש משהו. אין ספק, גם תראי את זה, זה לא...
אני אומר שכסף זה דבר שכל כך רחוק מהמקור, לא... המערכת הכלכלית כל כך מוכרת שאנחנו חיים בה, זה כל כך רחוק מהמקור, לכן אתה יכול לעבוד על אנשים ולגרום להם לחשוב שיש לך הרבה כסף, שאין לך הרבה כסף, אם אתה פורץ הרבה צפרים בקטנה.
אולי זה לא משתלט על העולם.
אם יש לך כסף ברמי של תקציב של ארצות הברית,
דבר ברוטים כזה או משהו. לכם דיון...
לא, זה נראה לי יותר הגיוני. זה ממש יכול...
אתה רואה כל כך לא שכסף, זה לא מעניין אותך. לא מעניין אותך.
לא, לא נכון, מה? תסתכל מה, אנשים עשירים ממש, מעניין אותם כוח.
אבל פה כמשקיעים אין לך את זה. כבר יש לך כל מה שאתה סתם, לשמור על העולם. Okay, so we continue on our quest to quantify Gaussianity. Okay, so we defined the moment, we defined this generating function of the moment, which is the expectation of value of x xt, looking at this function of t. And now I will define another function. G of t, which by definition is the log of f of t, or in other words, the log of the expectation value of e to xt over p x. And now let's take a Taylor expansion of this function. So I will call the coefficients of this Taylor expansion kappa 0, kappa 1, and so on. So G of t will be kappa 0 plus kappa 1 c plus kappa 2 t squared over 2 factorial, and so on. So remember, the coefficients of the Taylor expansions of S were simply the moments. The coefficients of the Taylor expansion of G are something else. And they are called cumulants. And therefore, G of t is called the generating function of the cumulant, which is just another way of saying that if you take G of t, take its Taylor expansion around 0, the coefficients are the cumulants. Now, what are these cumulants? So now one needs to do some work in order to relate them to the moments. And I will not do this work here, I will just tell you the answer. So if you start by asking, okay, but remember, G is just the log of F. So the task that if you want to find the cumulant, what is the relationship between the cumulant and the moment, we need to take this function and take the log of this function and expand it around 0, and we will write that as a power series of t, and then we will get some. We will be able to say what is the first order term, the linear term in t, and so on. So if you do this, you find that kappa 1 is simply equal to mu 1. In other words, the first cumulant is just the same as the mean. It's the mean of the distribution. And if you calculate kappa 2, you end up with mu 2 minus mu 1 squared. In other words, this is x squared minus x squared. This is also what we call sigma squared, or the variance. So the second cumulant is simply the variance. Okay? And it's possible to continue and calculate the next one. I will not write the expression. But from here on, I'm going to assume that just for writing the expressions, I'm going to assume that the mean is 0, just because the expressions for the next cumulants are a bit ugly, and I don't want to write them down in general. I want them to write them down in the case where mu 1 is 0, or the mean is 0. But by the way, one thing that I want to mention, I didn't write it down in my notes, but I will mention it now, is that if you take I would argue that the cumulants tell us something about the shape of the distribution. Like the variance, for example, tell us something about the width of the distribution. Now, if you look at moments, now imagine that you take a certain distribution and you just shift it you add to the value x some constant. You just shift the distribution. So that affects all the moments. But it does not affect the variance, right? And that's true also for all the other cumulants. All the cumulants, except for the first one, are insensitive to shifting the distribution, which is a good sign that they might tell us something about the shape of the distribution, Anyway.
Is a cumulant the same as a central moment?
Is it what?
As a central moment?
I don't know.
Isn't I don't know, right, the variance I think we call it central moment of the distribution, if you don't know the terminology.
Yeah, and I don't know. We can check. Okay, anyway, so from here on I'm going to assume, just for writing down the expression, that mu1 is equal to 0. And if it's not equal to 0 and you want to understand what will be the cumulant, you can figure it out by subtracting the mean. I will not do it. Okay, so then I want to write down explicitly the expressions for a few cumulants. So kappa 0 Kappa 1, if you assume that mu1 is 0, is simply 0. Kappa 2, in that case, is mu2, or in other words, it's the mean of x squared, which is also the variance. Kappa 3, in this case, ends up being just the same as mu3. In other words, it's the mean of x cubed. But kappa 4 is more interesting. Kappa 4 ends up, in this case, where mu1 is 0, ends up being mu4 minus 3 mu2 squared. So note that it's the mean of x to the 4 minus 3 times the mean of x squared squared. So note that it has units of, like each cumulant has the same units of the corresponding moments. This has units of x to the 4. Okay, now what is the significance of all? Why is all this interesting? So one of the main reasons why this is interesting is that it turns out for a Gaussian distribution, all the cumulants except for the first and second are 0. Okay? And this is why this is interesting for us. For a Gaussian distribution, all cumulants k n, where n is larger than 2, vanish. Let's prove this. Okay? So remember that f of t is the mean of e to the xt. And for a Gaussian distribution, I will write explicitly what this means. A Gaussian distribution, this is an integral dx from minus infinity to infinity. I need to write p of x. So p of x, and I'm going to assume zero mean Gaussian distributions for simplicity. So 1 over square root 2 pi sigma square x of minus x square over 2 sigma square. This is p of x, but it's all multiplied by e to the xt, so I will just add here xt. Okay, so this is f of t. Now, let's do a little sign calculation. Okay, how do I do an integral like this? I want to do an integral dx of minus x squared over 2 sigma squared plus xt. How can I do it? How can I do this integral? Yeah, okay, so we had a good proposal. If I had here an integral of, I mean, I know how to do the integral of a Gaussian. So if I can shift x such that what we will have here would be like the x minus something squared over 2 sigma squared, then I know how to do the integral. Let me explain. So what I want to do is to rewrite what we have here as follows. So here we have x squared divided by 2 sigma squared minus xt, right? I mean, it's the minus of this quantity. This is what I have here. And I want to write it, oh, actually, I should have x squared divided by 2 sigma squared minus xt. I want to write it as x minus something divided by 2 sigma squared plus something which will not depend on x, because then I can just take it out of the exponent. So what do I need here? I need here something that will give me, when I open up this square, I will have a term which is x squared divided by 2 sigma squared. And here I need something that will give me x times t. So obviously it has to be t here. And then what else do we need? If I just have here t, I will get minus 2 xt divided by 2 sigma squared. But I need xt. So I want to put here a sigma squared. And now, when we open up this expression, we'll have minus 2x sigma squared t divided by 2 sigma squared, so this is minus xt. So this is good, but we need here to, we will have another term, which will be this one, and we need to subtract it. So the term that we'll get from this squared will be sigma to the power 4 t squared divided by 2 sigma squared. So this is sigma squared t divided by 2. So I need to subtract that. So this is equal to this. Why is this good? Because now t squared, yes, sigma squared t squared. Because now it means that x of minus x squared over 2 sigma squared minus xt, which is what we have here, is the exponent of minus x minus sigma squared t squared divided by 2 sigma squared times the exponent of this. Okay, I mean I could put it here, but I can also write it as exponent like this, exponent of minus sigma squared t squared over 2. Now let's call this x theta. And I can do a shift of the variable x. X goes anyway from minus infinity to infinity, so x tilde also goes from minus infinity to infinity. And what else do I have here? I have the integral of the Gaussian. I mean, this part does not depend on x, so I just multiply everything. So I have the integral of the Gaussian, and I already have the normalization, the correct normalization in front here. So this whole integral will just be 1. And I will end up, therefore, with the exponent of minus sigma squared t squared over 2. Okay? But that's good because we now have an explicit expression for f of t. Remember that we need now to get the cumulant, we need to take the log of this. So g of t, which is the log of f of t, is minus sigma squared t squared over 2. And the cumulants, by definition, are the coefficients of the Taylor expansion of this as a function of t squared. So we can read out from this that mu1 in this case is 0. But this is because we set up initially, we chose a distribution with 0 mean. Mu2, I might have
some minus. I think it's plus.
yeah, because there was a minus.
Yeah,
there was a minus here. So it's a plus here. And therefore it's also a plus here and it's a plus here. So not mu2, mu1, kappa 1 is equal to 0, and kappa 2 is equal to sigma squared, and all the rest are 0. We don't have any t to the cube, t to the 4, and so on. So all the kappa n goes larger than 2 are 0. Good. So you see that for a Gaussian variable, indeed all the cumulants vanish. I mean, the part that I didn't show you is that again, that this is if you change the mean of, if you take a Gaussian with the mean other than 0, this is like shifting by some constant. This affects only the first cumulant. This is generally true. It affects only the first cumulant. All the other cumulants are not sensitive to that. So, for any Gaussian, that
the reverse is also true? If all the cumulants are beyond the 2.
yeah, because yes. So there's actually, in a sense, both the moment. If I tell you what are all the moments, if I tell you what are all the moments of a probability distribution, this defines the probability distribution, and that's true also for the cumulants. tell you, because there was a one-to-one correspondence between the cumulants and moment. So if I tell you what are the cumulants, that defines precisely the probability distribution, and therefore it's going to end up by being Gaussian. Okay, now all this is interesting for us. Yes.
You didn't talk about kappa 0? Zero?
For kappa 0, what is kappa 0? Well, you see that in this case it's 0, right? And I think maybe it's true in general that it's 0. Okay. Yeah, because look, I mean, this is what is kappa 0? It's the Taylor. I mean, it's the coefficient of the Taylor expansion when t is 0. I mean, it's actually the value of g of t when t is 0. So f of t, what is it when t is 0? It's the average of e to the 0, which is the average of 1, so it's 1. Right? F of t, when you take t equals 0, is 1. Log f of t, therefore, is 0 when you take t to be equal to 0, and therefore kappa 0 is 0. I didn't write it explicitly. Okay, now the reason all this is good is that now you see that we have some coefficients that somehow characterize the shape of the distribution, and they are 0 for a Gaussian distribution. And therefore we can use these coefficients as measures of non-Gaussianity. And as you'll see, we will use, in some sense, the lowest order cumulant, which is useful for us, which will end up not being kappa 3, but actually kappa 4. So the reason I want to give you some intuition to what the cumulants tell us. So let's talk about kappa 3 and about kappa 4. So one thing to note about kappa 3 is that it's completely 0 for many distributions which are non-Gaussian, but if the distribution is even, if it's symmetric around the mean, then kappa 3 will be 0. And that's why kappa 3 is not a very useful quantity for us to look at, because even for non-Gaussian distributions, it's often 0. But just to give you an idea for what it quantifies, so people define often a quantity called skewness of a distribution, and it's defined as follows. It's defined as kappa 3 divided by kappa 2 to the power 3 half. Now, I want to explain why this particular quantity. So, the skewness somehow measures to what extent the distribution is not symmetric, okay? But we want something which will be the same for if you take say this distribution, which is not symmetric, and you just expand it or squeeze it. We want a measure which will be the same. So by choosing this combination, remember that this has units of x cubed. The variance, which is kappa 2, has units of x squared. So by taking this combination, we get a dimensionless number. And so this number will be insensitive. If I take a distribution and I just squeeze it or expand it, it will have the same value. Okay? So this is why people use this particular definition. And I can also write it as, I mentioned to you that for a zero mean distribution, kappa 3 is simply mu3, and this is not mu. Okay, so just to give you an idea, for this particular distribution, you will get a skew is smaller than 0, and for this distribution, the skew is larger than 0, and for any symmetric or even distribution around the mean, the skew is precisely 0. The next quantity, which is that will be useful for us as a measure of non-Gaussianity, is something that people often call kurtosis. So again, first of all, remember, the first cumulant or mean is just the mean. Second cumulant is the variance. Tells us something about the width of the distribution. Skewness generated from the third cumulant is a measure of non-symmetry. And the fourth one that I want to mention is kurtosis. One thing to point out is that there's no one accepted definition of kurtosis, so people use this term, but sometimes they mean different things. We will use the following definition. It's going to be kappa 4 divided by kappa 2 squared. So again, it's dimensionless and it's invariant to stretching of the distribution, so it doesn't tell us anything about the width of the distribution. That's in kappa 2. It tells us something else. If you take the definition that I wrote before, you can see that this is also equal to mu 4, the fourth moment, divided by sigma 4 minus 3. By the way, for a Gaussian distribution, it's always true that mu 4 is equal to 3 times sigma 4 to the power 4, so 3 times the variance squared, and therefore the kurtosis vanishes. This is also another way of saying that the fourth cumulus is 0 for a Gaussian distribution. So we will work with this definition, and again I want to give you some intuition for what this somehow quantifies in the distribution by looking at some examples. So So let's take first a distribution which is uniform within a certain range. Okay, uniform distribution within a certain interval, not a Gaussian distribution. If this is P of x, then log P of x looks like it's minus infinity outside the interval, it's a constant within the interval. I won't do the calculation. It's a fairly simple calculation to calculate the kurtosis of this distribution, but so this is the uniform distribution. Turns out that the kurtosis, I will call the kurtosis K. So the kurtosis K for this distribution ends up being 1.2. For a Gaussian distribution, P of x looks like a Gaussian, log P of x looks like a parabola, and what the kurtosis, as we mentioned, is 0. Last example that I want to mention is a function called the logistic function. I will define it in a moment. And it kind of looks like this. It's more narrow in the middle than a Gaussian. It's more centered around the low values. So if I would plot the distribution, if I would plot log P of x, this is P of x, this is log P of x, and for the logistic function it looks kind of like this. So compared to a Gaussian, it has more weight on very small values, and also on the tail, it has a larger tail. Okay, and this is actually one of the reasons I'm mentioning this distribution is that many natural variables, many natural stimuli, if you measure the distribution, it's more similar to something like this than to a Gaussian. Okay? People sometimes say that this distribution is more sparse than a Gaussian distribution because you have a larger probability to have very small values. Okay? So it turns I didn't write exactly what it is. You know what? Maybe I should first write what it is. P of x 1 over alpha cosine, hyperbolic cosine of x over alpha. In a moment I will tell you where this is coming from. But for this function, which is kind of more narrow than a Gaussian, turns out the kurtosis is -1.2. So you see that this distribution, which is somehow more kind of spread than a Gaussian, has a positive kurtosis, and this distribution, which is somehow more narrow than a Gaussian, has a negative kurtosis. And by looking at these two examples, you might develop some intuition for what kurtosis measures as a deviation from Gaussianity. Now, I just want to, since I mentioned this probability distribution, I want to define it in another way, just so that you will know what this expression is coming from. So again, this is called the logistic distribution function.
The parameter is alpha?
The parameter is alpha, yes. And the kurtosis does not depend on alpha, because as we mentioned, the kurtosis is invariant to stretching. Or I mean, the only thing that changes if you change alpha is like rescaling of x. Kurtosis is insensitive to that because we took the fourth cumulant but divided by the second cumulant. Okay, so it's easier to, in some sense, to understand what this function is by defining it through its cumulative distribution function. So if I would think about p of x as an integral from -infinity to x of g of x prime, sorry, if I define g of x as the integral from -infinity to x of p of x prime dx prime, meaning that g of x is the cumulative distribution function of x, or in other words, f of x is g prime of x. So g of x has a somewhat more simple structure. G of x, in this case, is half plus half hyperbolic tangent of x divided by alpha, meaning that the cumulative distribution function looks like a kind of a sigmoidal. It starts from very negative values of x. It's 0, right? Because then the hyperbolic tangent is -1. And then for large values, so it's 0 here. And for large values of x, it's 1. And it kind of goes like this from 0 to 1 over a range which is given by alpha. So this is the cumulative distribution function. Meaning that the interesting thing for x, I mean, it happens in values between more or less orders minus alpha and alpha. And the variance of this distribution, just if you I have it written in my notebook, so I might as well, I don't know why I wrote it, but I might as well tell you that the variance of this distribution is pi squared alpha squared divided by 12. Anyway, the kurtosis ends up, if you calculate it, it's not difficult to calculate it. The kurtosis of this distribution, as I mentioned, is -1.2. Now, the last thing that I want to point out is going back to this vague claim that I wrote before, that if you combine variables which are not Gaussian, you end up with something which is more Gaussian. I want to use now the kurtosis as a measure of that. So what I want to show you is that if you have two variables with the same distribution, I mean this is something that you brought up, which correctly, if they have the same distribution and they have some non-zero kurtosis, and you mix them, you'll end up with something which is smaller kurtosis. Okay, meaning that you're closer to the Gaussian.
So it's only the fourth. What about the higher cumulate? You don't know.
I don't know. Actually, I don't know if I mean
No, you don't know that there's a 0. You know that
That's
tau
right.
is 0, but you don't know that.
That's true. That's true. But I will only discuss the kurtosis.
Okay.
It's true also that I mean the central limit theorem tells us that when you combine many variables, all of the cumulants will go to, with although larger than 2, will go to 0. But I'm not sure whether when you combine 2, it's easy to prove that it always equals 0. So let me just show you that. Okay, so imagine that S1 and S2 are two independent variables. With the same distribution. And P of S is some function. It's characterized by a certain sigma square, certain variance, and a certain kappa 2. Kappa 2 is not a kurtosis, kappa 2 is kappa 4. Yeah? Which is the fourth cumulant. And now imagine that I take any linear combination of these two variables, alpha 1 S1 plus alpha 2 S2. Okay? And what I want to show you is that the absolute magnitude of the kurtosis will go down. Okay? Meaning that we're closer in that sense to a Gaussian variable. So sigma square of x, the variance of x, well, when you combine two independent variables, when you sum two independent variables, the variances add up, right? So the variance of x is simply going to be alpha 1 squared times the variance of S1, which was sigma squared, plus alpha 2 squared times the variance of S2, which was also sigma squared. So it's alpha 1 squared plus alpha 2 squared times sigma squared. What about the fourth cumulant? So the fourth cumulant of x, I will not prove, but it's also additive in this case. So, but additive with the power of 4, because just by the fact that the fourth cumulant has dimensions of x squared, it's easy to see that if I take alpha times s, the kurtosis of alpha times s will be alpha to the power 4 times, not the kurtosis, the fourth cumulant, kappa 4 of alpha times s will be alpha to the 4 times the fourth cumulant of s. So, but also, if you take two independent variables, the fourth cumulants add up. So this is going to be alpha 1 to the power 4 times kappa 4 plus alpha 2 to the power 4 kappa 4, or in other words, alpha 1 to the power 4 plus alpha 2 to the power 4 kappa 4. And now the kurtosis remember that the kurtosis was defined as the kappa 4 divided by sigma to the power 4. So it's going to be alpha 1 to the power 4 plus alpha 2 to the power 4 divided by alpha 1 squared plus alpha 2 squared to the power 2 times the kurtosis times kappa 4 of s divided by sigma to the power 4 of s. Or in other words, it's alpha 1 to the power 4 plus alpha 2 to the power 4 divided by alpha 1 squared plus alpha 2 squared times the kurtosis of s. Okay? And this number, whatever way you choose alpha 1 and alpha 2, it's always smaller than 1. It's positive and it's always smaller than 1. Okay, so we'll end up with a kurtosis which has the same sign as the kurtosis of S, but it will be smaller. Okay, so this is a nice formalization of something that I told you, that we we have some measure of Gaussianity, kurtosis. Small kurtosis means more Gaussian. We take two variables which are not Gaussian, we mix them up, and we get something which is more Gaussian in this sense. And therefore, our assumption would be that the mixing up of our sources has decreased the kurtosis, or the absolute magnitude of the kurtosis of our observations. And one approach to look for the demixing matrix is to look for such a demixing matrix that will maximize, after you will demix, you will get variables with maximal kurtosis. Okay? And this is an approach that you will explore in a homework assignment, which is very fun to do because you get some images which are mixed up and you don't know what are the coefficients, and you manage to find the coefficients and get, separate the images perfectly, and we could have done it also for the auditory stimuli. Now, one of the things that I want to mention now before we finish for today is that if you look at visual stimuli, actually I don't need to draw anything new because I have it here. If you look at visual stimuli, so you take an image and you just do the statistics of the distribution of the pixels, okay? Subtract the mean, okay, so that would, like this, it will be around 0. If it was Gaussian, which is what we assumed when we discussed the retina, and suppose that you take the log, the probability distribution of the log. If it was Gaussian, you would have a parabola, right? But take an image and do it. You will see that it's not what you get. You get something that looks much more similar to this. Okay. And so one of the theories of encoding in the visual cortex, which was done by Olshausen and Field, and more or less concurrently, somewhat different interpretation by Senovsky and Bell, was that the visual cortex uses such receptive fields that extract the independent components of images. Now, as I mentioned to you, true images are not linear combinations of independent components. Nevertheless, we can imagine that they are, and to apply some algorithm that is supposed to find the independent components, and when we do that, this algorithm finds that the filter that you want to apply are Gabor filters. And then after you do that, you get something which is even more, even less Gaussian. I mean, it is even more pointy like this. It's more Gaussian than the original pixels. It's more un-Gaussian than the original pixels that you look at. Okay, I think that we will end. So I'll just tell you a bit about the rest of the course. First of all, we have 3 more weeks, and I think I will continue to have an extra hour in all of them. So maybe the last one is optional if it's not part of won't be part of the exam, but I just want to cover enough material, and we lost many hours. So we have 3 more weeks, which are like 4 weeks because of the extra hours in terms of how much time we have lectures. And I think next week I will spend maybe another hour talking about ICA because there's still a few more interesting things to say. And then we switch to a completely new topic, which is supervised learning. So this is learning in which you are shown a set of examples and you are told how you are supposed to categorize them. Or that it's a binary categorization. You have to, some of them belong to group A, some of them group B. You are told what are the correct answers, what can you learn from these examples and how to do that. And so that will be the rest of the course.
שכחנו רק במקרה שהם אידנטיים, נכון? כאילו, זה יכול גם ברמת העיקרון?
זה מתחיל להיות ממש לא ברור, יש לך סוף שחקן כל היד באופן תיאורטי, שכולנו הסתגלות דומה, אולי לא זהה, אבל משהו באופן דומה, בנאצ'ו
בדרך למעבדה, כי אתמול שכחתי שם.
יש להם הרבה פתיח ויש זנב ארוך. אז במקרים כאלה זה בדרך כלל נכון, הרבה אותם. אני מתקרב את זה אפשרי.
כללי, בעיקרון יש איזשהו קשר באמת בין המודל לבין חילופי פוריה אתה יכול להגדיר
זה כמעט ככה, כי
כן, זהו. כן.
דברים כאלה שזה...
זה מתוך שיש קשר גם
כאילו, בסך הכל מגדיר לנו סימטריות כאילו של הפונקציה, כמו שפוריה מגדיר לנו את הסימטריה כאילו של איזה דברים אנחנו רואים אותם אותו דבר ואיזה אנחנו לא רואים אותו דבר, נכון? זה כאילו...
האמת שאני חייב להגיד שהדבר הזה בפני עצמו, הקומולטים יש לי בדרך כלל לא שמעתי, הקומולטים יש מפתחים את התשובה שלה.
אני מסתכל על זה טעות, זה מין כזה, כאילו, לפחות על פוריה, זה מין הרוחב פס שאתה יכול להעביר, כאילו... תודה.
I wanted to ask you about the proof for the cumulant point to the for the Gaussian.
Yeah.
So you said f of t is equal to the expected value of exactly. So x here is the Gaussian distribution?
Exactly. So what I wrote here is if you want to add the missing link here is that this is an integral of p of x times p of xt. P of x is what I wrote here.
Okay.
But here you were missing, x of xt.
Okay. So ext is the entire thing.
Times x of xt, but then you can put it inside the exponent. So here you should have had x, this x times x of xt, or e to the xt. Maybe, why don't you correct it already?
Yeah.
Something
yeah.
Just put an e below it, and it will be e to the xt.
Right to the x times.
Okay, so this is clear to you what's the connection between this and this?
So this whole thing is p of x.
So this, by definition, this is the average of p of x of e to the xt.
And this is multiplication.
Yeah. But now this is an exponent times an exponent, so I can just put the xt inside here. And then
okay. So I just need parentheses. Like this. Okay.
Yeah, that's
so, okay.
I think there is a seminar today. There's happy hour. What time is it supposed to set up? Yeah. Carmel, are you hanging around?
For how long?
What was on?
No, I think it ends at 3. I have an hour and 10 minutes. Do something.
I need to buy printer ink and dumbbells. That's my shopping list. Carmel, are you staying for the seminar? I don't know about that. I don't know what the topic is.
Even I don't know. I just have no idea. Said that they are doing behavior
Portable like it.
Yeah.
Okay, that makes sense.
So maybe the experimental procedure. This is about new technique that is.
And you
around this way or this way, then you have a chance of not being there. But on the other hand, I don't want to be among the first and I don't know where he's at. So I'll send somewhere in the middle. And then he just goes, boom.
I was sitting last time also at the same place. But I was noticing when people are entering, they first looked at that side and then they decided where to sit. Almost everyone. They enter, look at that side and then decide.
Yeah, because you don't want to be first. But then he decides suddenly randomly.
Yeah, well, I don't know. I really didn't want to be the first figure, and I really didn't want to. I didn't want to be the first figure in the first paper, and I didn't want to be the last figure in the last paper.
Yeah.
Because those ones I did. Oh, no one's in the middle. We're like, okay,
Yeah.
it's the basic idea of the paper.
That's exactly what I thought. That's why I sat in the middle, and then he like nearly pointed at me with like 2 spaces to the left, to the right, and then it was funny because he started saying, and then we'll go this way, like our way. You know what? No, we'll go the other way. And we were like,
I love the one with Yair's turn, and it's just like a... Fantastic.
It was good. Yeah. I already talked to him. Still, we were waiting for another meeting with him. Because it was only with Elon. In general, he was